Hey folks, welcome to the Simple Harmonic Motion unit. This unit goes pretty quickly, and there's lots of mini lessons in here. So the first lesson is about oscillations and the idea of a restoring force. So we've studied things that oscillate before when we studied circular motion. If something continuously goes around in a circle, it's actually oscillating. So any oscillation is a back and forth motion around a central point. It does not have to happen at regular intervals. So there's no real constraints. However, for the types of oscillations that we are talking about, they have the following properties. So I will demonstrate oscillations in a couple minutes here, and there's really two that we're focusing on in this unit, but let's go through the properties. Period and frequency you are already aware of. So period being the time it takes for one oscillation. That's the same. So period is always a measurement of time for one event that happens. It could be something moving in a circle, but it doesn't have to be. And so we'll talk about the period of motion of a spring that's oscillating and a pendulum that's oscillating. Because oscillations have a period, they also have a frequency. So remember that these are reciprocals of one another. So frequency is the number of oscillations per second, and period is the time for one oscillation. So the frequency is always the 1 over the period, and the period is always 1 over the frequency. Amplitude is relatively new. I think we saw it in a couple of problems, but amplitude is the maximum displacement that an object that's oscillating has relative to the central point. We often refer to that as the equilibrium point, but central point's pretty good. Amplitude is a measurement of meters, and generally it's measured from the middle out. And so the amplitude for an oscillation that we're going to study, the amplitudes are the same no matter which direction you measure them. So there's like a positive amplitude and a negative amplitude for something that's oscillating. And kind of the main event for today is this idea of the restoring force. So as things are oscillating, the reason they oscillate is because of a restoring force. Whenever they move away from the central point, there's always something pushing or pulling them back toward that central point. And so that's what we mean by restoring, that the force is acting to restore the object to equilibrium. But since that doesn't happen, the force actually ends up causing the oscillation to continue. And we actually know the equation for one of the restoring forces that we're going to study. And so it's Hooke's law. So when we did the energy unit, we studied springs. And very briefly, or maybe even not at all, I introduced the idea of the spring force. Hooke's law describes the restoring force of a spring. So the equation as written in your equation sheet is the absolute value of the spring force equals K times the absolute value of X. So I think you have definitions for these already, but just in case you don't. Fs is the spring force, so in newtons. X is the amount of stretch. And so I have, I can demonstrate this with a spring. And I've done this before, but here's a spring. This is a spring that has a stretch right now of 0. But as soon as I pull on it, I am changing the length. So if I measure this length, stretch it, measure this length, and find the difference between those two measurements, that's what the stretch is. And so that's the value of X. Now this spring, because of the way it's manufactured, can only be stretched outward. Many springs, if there's space between the coils, can also be compressed, and Hooke's law follows the same idea. The reason why you have these absolute value symbols is because the direction of the spring force is actually always opposite the direction of the stretch. So you can feel this if you take a rubber band and start to pull it. As you stretch a spring, if I exert a force to increase the length, the spring force is acting to decrease the length to always get back to equilibrium. So this is equilibrium for this spring because the coils are all touching. And now, as soon as I stretch it, it's out of equilibrium. And so the force of a spring is always acting to restore the spring to its original length. Now, because I'm pulling with both hands, you have to recognize that there's a spring force on my right hand that points to the left, and a spring force on my left hand that points to the right. And so the spring force pulls or pushes in opposite directions at the same time. Now, the K is the force constant. And so the idea behind K is it's the strength of the spring. So this spring has a relatively low force constant. It's really easy for me to pull this spring, but if I had to exert more force to produce the same result, then that's a function of a greater value for force constant. So again, like the larger the value of K, the more force it takes to stretch a spring by a certain amount. And so basically, based on how it's manufactured, some springs are like very pliable like this, and some just aren't. So the way that that shows up, and the way that you're going to want to think about this the most, is this equation is basically a linear function. And so it fits with the form of y equals mx plus b. Now, the way that it's typically done, it's not done with this equation. So it's just saying that the spring force is equal to k times the stretch. And then if the spring isn't stretched, then there's a force of 0 on the spring. So, in a graph, the y-axis is the force, the x-axis is the stretch, and then most critically, the slope of the line is the value of k. The greater the slope of the line, the larger the k value, the faster that force ramps up with the stretch. And because k is the slope of this, rise over run would be newtons over meters. So in case you've forgotten, the value of k is in newtons per meter. So we'll be working with Hooke's law in the lab. And for now, I just wanted to demonstrate the spring and the pendulum for you. So I'm going to pause this and rearrange my setup here and restart when I'm ready. Okay, so here is the pendulum setup. Now I'm going to just move my camera for a second, but I'll return it to there. So the pendulum is just like it's a bar, a cross bar that's attached to my desk, and just a string. And then there's a mass at the bottom. This is a 50-gram mass. And so you've seen a pendulum before, and this is what it does. It swings back and forth. And this is a special kind of oscillation. It's one that happens with great regularity. And so the period of the pendulum is a constant value as it oscillates. And if I were to hold this bar steady, it wouldn't slow its oscillation, or rather the oscillation wouldn't get smaller and smaller. So some of the properties of the oscillation, if I start this pendulum here, I let it go, and if I wanted to time the oscillation, I would start my stopwatch when the pendulum was over here, and I would stop it when the pendulum returned to there. So that represents one complete oscillation for the pendulum. So it starts over here, moves all the way across, and then comes back, and that is one oscillation. And so that amount of time is going to be the period. The other aspect that we talked about is amplitude. And so this would be like a low amplitude oscillation, and then this would be a high amplitude oscillation. Now, for a pendulum, technically there's two ways you can represent amplitude. So, there's like a vertical, and if I rotate this a little bit, you can see like the string and the bar behind it line up pretty nicely. So amplitude could be a measurement of essentially this distance. So literally, if I held up a ruler, what distance away from that bar's vertical is this pendulum? So that's one way to represent it. And then the other way is you can see in this picture that like the string is at an angle. So I could go all the way up to the top of the bar, and I could measure like the angle at which the pendulum is being held, and that's also a representation of amplitude. So there's two ways to do it with a pendulum. The last thing is the restoring force. And so hopefully you remember from energy that gravity is the thing that's going to cause the pendulum to swing. If I hold it up here and let it go, gravity takes hold. So the restoring force on a pendulum is the force of gravity. And so we will investigate pendulums more later. But for now, just know that it's gravity that is the restoring force. Okay, so I'm going to pause this again, get the spring going, and then we'll talk. Okay, last up is the spring. And so here's the spring sitting here. Now this is like a very jiggly scenario, so there's lots of energy loss when this happens, but here I have a vertically oriented spring. And so right now, even though it's hanging and being pulled by gravity, there's no stretch in that spring. But if I put a mass on it and let it fall, the spring will eventually come to rest. And again, if I measure the change in length of the spring, I'm measuring the stretch. And if I know the mass, I can actually infer or calculate what the spring constant is. And so, it should make sense that the more mass you put on, the further it stretches. And so now, like, the spring is stretching further than you can see. But the more weight you put on, the greater force there is downward on the spring, and so the further the spring will stretch. So that's one aspect that is specifically related to Hooke's law. But as far as the oscillations go, if you like put this back up to the top and let go, and if I hold it steady, you'll see the spring oscillate up and down. And so similar to the pendulum, the oscillation of the spring is the amount of time it takes, let's say, from the spring to be as compressed as possible until it goes all the way down to the bottom and then comes back up again. So this oscillation, if I could possibly hold this bar steady, it would be a constant value for a really long time. Even if the oscillation dampened or damped, got like a smaller and smaller amplitude, the oscillation would still have the same period. Now, one last thing about this length right here is the equilibrium length of the spring. So if I kept track of like this height and allowed it to do that, if I record this, which I'm doing now, and I paused it here, the difference in height between those two moments of the spring would be the amplitude. So again, the spring, if you put a mass hanging from a spring, it has its own equilibrium length, and then any deviation from this represents an amplitude that's either negative or positive. So these are the things that we're investigating with springs and pendulums.